So what is a vector space? Well, it's a set V with operations on it. So first we need a nice addition, and I'll say more about what nice means. We also need a nice scalar multiplication. And finally, we need the addition and the scalar multiplication to be, well, compatible. They need to play nice with each other. So you can follow along in the definition on page 190. What I'll try to do is give you more of a different way to look at it. So first, we need an addition. That's commutative, associative, binary operation on the set V. So let's go through this and see what that means. So it's a binary operation on V. So I need to take as input a pair of elements in V and output an element in V. So this is a map from V cross V to V. It's a rule so that U plus V is in V for all U and V in V. Now we need it to be commutative, so I want U plus V to equal V plus U for all vectors U and V. I want it to be associative, so U plus V plus W is equal to U plus V plus W. And this is for all vectors U, V, and W. So this is items 1 through 4 in the definition on page 190. There's a few more properties we want the addition to have. Identity and inverses. So we need an additive identity. So there's a 0 vector, denoted 0, that has the property that U plus 0 is equal to U for all vectors U. We also need the existence of inverses. So for every vector U, there's going to be a vector minus U in the space, and it's going to have the property that U plus minus U is the identity vector, the 0 vector. So this is items 5 and 6 on the definition on page 190. Next, we need a scalar multiplication. And so what is that? Well, it's going to take as input a scalar and a vector and output the scalar multiple. What properties do we want this to have? Well, for all scalars C and D, and for all vectors U, I want C plus D times U to be the same as C times U plus D times U. And so it's like I want the scalar multiplication to distribute across regular addition. I also want C times D times U to be the same as C times D as scalars times U. And finally, I want 1 to behave like a 1. So I want 1 times U to equal U. And this is items 6 and 8 through 10 on the definition on page 190. And finally, we want these two operations to play nicely with each other. So for all scalars C and all vectors U and V, if I scale U plus V, I want that to equal C times U plus C times V. And this is item 7 in the definition on 190. And so a vector space, on one hand, it's just this very abstract object, but on the other, it's just any set with these operations that satisfy these properties, right? And the benefit here is it's any set with these operations. And so we can apply these linear algebra techniques that we're learning to a wide variety of problems. And so the trick, as the semester goes on, will be taking a hard problem, translating it so that we understand that it has an incarnation that lives in some vector space so that we can apply linear algebra techniques to solve it.